AB Calculus 2.6, day number 1. Goals for today's video are to understand continuity, know the definition and how to apply it, find points of discontinuity, look at what's called left and right continuity, knowledge of what functions are continuous, composition of continuous functions, and then the intermediate value theorem. Throughout this course, you will see the intermediate value theorem referred to as IVT. Okay, so an opener. What do we mean when we say a function is continuous? So here's the formal definition of continuity. Continuity at a point. A function f is continuous at a point A if the limit as x approaches a of f of x equals f of a. If f is not continuous at a, then a is considered a point of discontinuity. So here's a function where f of x is continuous at x equals a. Okay, because the limit as x approaches a, which we could say would be, I don't know, for example, 1, is equivalent to f of a. All right, here's an example of a discontinuous function, or a discontinuity at x equals a. Where the limit as f of x approaches a might be, I don't know, 2, but the actual value for f of a does not equal 2. Now it could come in this form. It could also be shown in a situation like this, where f of a is not equal to the limit as x approaches a. So the continuity checklist is a big one. Let's get started on that. In order for a function f to be continuous, f of a must exist. The limit as x approaches a of f of x must exist, which means to the side here that the limit as x approaches a from the left of f of x is equal to the limit as x approaches a from the right of f of x. That's how we would prove or show that the limit as x approaches a of f of x exists. And the third thing is that the limit as x approaches a of f of x is equal to f of a. So it kind of plugs that gap. All right, let's look at example 1 here. I've got a graph of f here. I'm going to find these first 3 values. F of -5 looks to be 6. F of 2 is 1. F of 4, let's assume that this is f of 4, would be -3. Okay, so let's look at first some limits as x approaches certain values for f of x. So as x approaches -7 from the left and the right, it looks like those agree, and the limit as x approaches -7 would be 2. The limit as x approaches 4 of f of x, as we analyze from the left and from the right, those two values, outputs do not match. Therefore, the limit does not exist. How about the limit as x approaches 0 from the right? It looks like our function as x approaches 0 from the right will go up without bound. That'll be positive infinity. And the limit as x approaches -infinity of f of x, it looks as if it's approaching a horizontal asymptote here at y equals 0. So there would be a horizontal asymptote for f of x at at y equals 0. All right, let's move over to column 2. Limit as x approaches -5 of f of x looks to be 6. And that's because the limit from the left and the limit from the right match. Okay, the limit as x approaches 0. Well, the limit as x approaches 0, of course, the left-handed limit and the right-handed limit do not match. The left-handed limit looks to be a -infinity, and the right-handed limit we had considered over here. Therefore, the limit as x approaches 0 does not exist. Okay, let's look at the limit as x approaches 4 from the right. So 4 from the right, coming here, looks to be -3. as x approaches infinity, f of x approaches the horizontal asymptote it looks to be right here at y equals 0. And a couple more limits. Limit as x approaches 2 of f of x, even though f of 2 is not equal to the limit still exists and therefore is 3. And the limit as x approaches 4 from the left, one more time here, looks to be 2. So some practice there with limits. Okay, let's continue on here and look at the definition of continuity using these values that we've just determined. So it says, use the definition of a continuous function in the continuity checklist to complete the following statements. So looking at part A, f is not continuous at x equals -7. Okay, so let's look at the items that involve limits as x approaches -7. Okay, well, I guess I should scroll up to the graph. As we approach -7, we have to consider, does f of a exist? Okay, that's the first part. Second, does the limit as x approaches a of f of x exist? And then are those two things equal? So is f of a equal to the limit as x approaches a of f of x? All right, so once we hit an issue with any one of those three criteria, we can say that the function is not continuous at the value. So as I look at the function at x equals -7, well, I don't see an output. Therefore, f of x is not continuous at x equals -7 because f of -7 does not exist. So that's a violation of the first of the criteria. Okay, let's look at part B. F is not continuous at x equals 2. Okay, so as I look at around x equals 2, well, the limit exists and the value exists, but the limit does not equal the value. So that's a violation. Okay, f of 2 does not equal the limit as x approaches 2 of f of x. So that's a violation of criteria number 3. Even though 1 and 2 are satisfied, 3 is not. How about part C? F is not continuous at x equals 4. Well, that's an issue because the limit doesn't exist as x approaches 4. So because the limit as x approaches 4 of f of x does not exist, we got problems. So that's a violation of part 2 of the continuity checklist. Okay, let's continue on with this idea of continuity. Okay, in example 2, we've got 4 parts. We're going to look at each of these functions and determine if the function is discontinuous at a point, and then use the definition to tell us why there's a violation there of the continuity checklist. Okay, so f of x in part A is x squared minus x minus 2 over x minus 2. So if I were to take the limit as x approaches a certain value, where would there potentially be an issue? Well, I'd see a vertical asymptote at potentially at x equals 2, right, as I look at the denominator, but actually there's a hole there. So if you factor the numerator, you get x minus 2, x plus 1 over x minus 2. What that means is that f of 2 does not exist. Therefore, there's a discontinuity at x equals 1, x equals 2, since f of 2 does not exist. Okay, let's look at part B. F of x equals 1 over x squared when x is not equal to 0, and 1 when x equals 0. Okay, so I'm going to say that there's a discontinuity when x equals 0, and I'm going to show you graphically why that is. Okay, so 1 over x squared, I'm going to put that in blue. It's going to look like this. And 1 when x equals 0 will look like that. Okay, so I've got a problem here, right? I suppose you could say that on the checklist, 1 is satisfied because f of 0 equals 1, but 2 is not satisfied because the limit as x approaches 0 of f of x, it doesn't exist, right? And the reason for that is because the left-handed limit and the right-handed limit are infinite limits. And therefore, we can't say that those are equal. Therefore, our violation, of course, is right here in part 2. So we won't even get to the third portion of the continuity checklist. Okay, let's look at part C. In part C, this is kind of interesting. We look at f of x, and it's this piecewise function. So what I'm going to do is I'm going to utilize what I know from part A, which is that on this portion of the graph, f of x actually will behave like x plus 1. Right? Now the question at hand is, will this plug that discontinuity? Will it plug that discontinuity? And we'll see. Let's look at it. So in part 1 of the continuity checklist, does f of 2 exist? Yes, it does. It equals 1. Part 2, is the limit as x approaches 2 of f of x exist? Well, let's look. Let's look at the one-sided limits. So limit as x approaches 2 from the left of f of x, the limit as x approaches 2 of f of x will be equivalent to x plus 1 with a 2 inserted. So we would insert a 2 plus 1, and it equals 3. Now part 3, we got a violation. So there will be a discontinuity here because f of 2, which equals 1, is not equal to the limit as x approaches 2 of f of x, which is equal to 3. So because f of 2 is not equal to the limit as x approaches 2 of f of x, then therefore f of x has a discontinuity at x equals 2. Typically when you see a piecewise function, just so you're aware, the discontinuity or whatever you should be checking will happen at that value. Okay, now of course we've got the greatest integer function here in part D. The greatest integer function has problems everywhere with continuity, and it's going to happen, you'll see here, at each of the integer values. So at 1 and at 2 and at 3 and at 0 and -1 and etc. There will be a discontinuity at every integer value. Okay, let's continue and talk about right and left discontinuity. All right, so explain why the function below is discontinuous at x equals -1. Sketch the graph of said function. Okay, so first thing, let's just go off the checklist. Does f of -1 exist? Yes, it does. And it actually comes from this portion of the piecewise. So I'm going to plug in a -1 and I get 0. Okay, that's great. So now we have to answer, does the limit as x approaches -1 of f of x exist? Well, I can do that two ways, graphically, or I can look at right and left limits. So I'm going to first look at right and left limits. So I'm going to write the limit as x approaches -1 from the left of f of x. When I do that, I'm going to be utilizing the first part of the piecewise function. Therefore, I'm going to insert a -1, which is -1 minus 1. So that'll be -2. So the limit as x approaches -1 from the right, we're going to see if that'll be equivalent. Well, we know that won't be equivalent because we've already actually found that value in part 1 of the discontinuity check, or the continuity checklist. Right? I took -1, and I added 1, and I got 0. Therefore, this limit in part 2 of the checklist will not exist. Thus, we won't have continuity for this function. Now let's graph this. I'm going to graph the first part of the function in green and the second part in red. So what we'll see is that the value exists at x equals -1, but the limit doesn't exist at x equals -1. So I'm going to sketch x plus 1 when x is greater than or equal to -1. So x plus 1 will go through its y-intercept at 0, 1, and will equal 0 when x is -1, and will contain all points greater than or equal to -1. Okay, and then of course we'd have a function x minus 1 when x is less than -1. Well, we know that the output is -2 when x is -1, and then the function obtains all outputs along that line when x is less than 1. So you can see the discontinuity here, right? We can see that the value exists, the limit from the right and the limit from the left exist, but the limit doesn't exist at that value. Okay, a function is considered continuous from the right, okay, in this case, or in any case for that matter, if f of a equals the limit as x approaches a from the right of f of x. So that just means the limit equals the value coming from the right. In this case, it does. This is a prime case for right continuity, or continuity from the right, because the limit coming from the right of the function is equal to the value at that x value. And the exact same for the other side. F of a is, or f is continuous from the left at a if f of a is equal to the limit as x approaches a from the left of f of x. So with the greatest integer function, if we were to continue to look at that thing, it's our buddy, all right, we would see that this function is right continuous. Okay, it's right continuous at each of these jump points, right, because the function's limit coming from the right is equal to the value on each of these steps. Okay, so let's talk a little bit about a couple of different types of discontinuities. All right, so this isn't part of the notes, but I'm just gonna play with this a little bit. Types of discontinuities. I don't know how to spell. Okay, there we go. So you've got your removable. Okay, a removable discontinuity looks like the following. I've got a graph of a function. Here's the function, and here's the output. That's a removable discontinuity. Then you've got a jump discontinuity, like the greatest integer function, or like the function we saw in the previous example, where you have a jump like that. There's a jump discontinuity. And then this doesn't typically have a special name. However, when you have an asymptote, I've seen, for example, if we have an asymptote here at, vertical asymptote that is, at x equals 0, this is many times called a essential discontinuity. I'm just going to stop right there. Okay, many times it can be a time saver for you on an exam, especially in May, if you just know which functions are continuous everywhere or on their domains. Okay, so certain functions are just good to know. So polynomials are one. Polynomials are continuous for all real numbers. Okay, and of course, within that polynomial family are lines. So lines, you don't have to worry about discontinuities. Exponential functions. Okay, those are also continuous on the real numbers. All right, sine and cosine, sine x, cosine x, also continuous for all real numbers. And these, I would just note that for all real numbers, those functions are continuous forever. Okay, there are certain functions who are continuous on their domain, which you want to be aware of. So like logarithms, so log x and ln of x, as well as the square root function. Okay, square root function is also continuous on its domain. So you just want to be aware that there are no discontinuities within the bounds of the domain of those functions. And of course, for 1 through 4, there are no discontinuities at all, unless you start getting into rational functions using those. So be careful with that. All right, let's talk about composite functions or compositions of composite functions. If g is continuous at a and f is continuous at g of a, we're allowed to use this manipulation. Okay, so the limit as x approaches a of f of g of x, you can simplify by taking the limit as x approaches a of g of x and then taking that value and plugging it into f, provided, right, that f is continuous at that value g of a, so that f doesn't have a discontinuity there. So if the limit as x approaches a of g of x is equal to L and f is continuous at L, then that works. That's true. Okay, we're coming up on one of the more important theorems that you'll see this semester, and this year for that matter. It's called the intermediate value theorem for continuous functions, okay, referred to typically as IVT. All right, now one of the first things you need to be aware of is that in order for this theorem to apply, the function must be continuous on the interval. Okay, and you can see that that's underlined and bolded here. So let's read through the intermediate value theorem. A function y equals f of x that is continuous on a closed interval from a to b takes on every value between f of a and f of b. Okay, in other words, if y sub 0 is between f of a and f of b, then y sub 0 equals f of c for some c between a and b. Okay, so let's make sense of that. All right, here is the x value a, and this point is the point a f of a. So here's the output f of a. And here is the x value b, the point b f of b, and of course here would be the output f of b. Okay, so now seeing this range of values between f of a and f of b, I want to highlight two different portions of the graph and show you, first of all, this portion of the graph, and then this green portion of the graph. All right, it might not be as easy for you to see as it is for me. However, the distinguishing part of this is that the yellow portion of the graph, those outputs, are not between f of a and f of b, but the green portion is, and therefore there is a range of possible c values. C is somewhere in that set, so there exists a value c such that f of c is between f of a and f of b. Okay, that's what the intermediate value theorem is telling us. All right, so if I pick any c value or any x value and call it c in this interval, its output would be between f of b and f of a. Now, it doesn't mean that every x value between a and b would have an output between f of a and f of b. As we can clearly see from a to this purple dot here, any x value chosen in here would be outside of that interval from f of a to f of b. Okay, so let's look at an example of this using the intermediate value theorem to show that there is at least one root of the given equation in a specified interval. So what does it mean to have a root? A root is where y equals 0. So there's some value c such that f of c has to equal 0. Okay, so there's essentially three things that you want to do. First thing that we need to do is we need to know that the function is continuous, otherwise the intermediate value theorem doesn't apply. So since f of x is a polynomial then it is continuous. I'm going to abbreviate here, continuous on the real numbers. Therefore, f of x is continuous on the interval from 0 to 1. Okay, cool. Check. We know it's continuous, therefore the IVT applies. Okay, the second thing that you want to do is you want to find outputs on the endpoints. So I want to find f of 0, and I want to find f of 1. So it looks like f of 0 equals 1, and f of 1 would equal 1 minus 3 plus 1. So f of 1 equals negative 1. Okay. So thinking about that now, I've got a function, f of x, where f of 0 equals 1, and f of 1 equals negative 1. And I know that the function is continuous on the interval from 0 to 1. Okay, so clearly, if I were to join these two in any fashion, say the function joins or looks like that, right? Then by the intermediate value theorem, there exists a C between 0 and 1 such that f of c is equal to 0. Okay, so what is that c value? I have no idea. I don't know. But I do know that I get the point here, c comma 0, which means that f of c equals 0. Now, the function could do something else. I'm not necessarily concerned about what other possible options or orientations this function could have, but I mean, the function could do something like this, and I don't know if it does. Honestly, I didn't check graphically, but it could look like that, right? So this could be a graph of f of x, or this could be a graph of f of x. But the intermediate value theorem, the key thing is that there could be at least one point, right? At least one root. Okay, in this case, if I were looking at this graph, there would be 3 c values, right? We could have c1, c2, and c3 in that order, right? So the intermediate value theorem in this case requires you to show that the function is continuous, find the endpoints, and then the third step, like we did right here, is to use the intermediate value theorem to give a justification for why it satisfies the question. All right, guys, that's it for 2.6, day number 1. See you in the next video.